Okay, so I'm going to make a couple videos here going through a complete AP exam. So I'm going to start with the multiple choice. It's going to take probably a few videos to get through the entire multiple choice section, and then a couple videos to get through an entire free response. So I'm going to do them in installments. I plan to get them done in the next couple days. So as we lead up to your final exam, and the AP exam. All the videos will be posted, but I can't guarantee I'll get them done by this weekend, but they will be done before next Wednesday, your final exam. So I just want to, we're going to start with a multiple choice test. So those of you that are doing a lot of the practice tests, this is practice test number 3 in class. So this isn't one of the multiple choices that you have on AP Classroom available to you. This is one of the tests that I have in the classroom, and this would be multiple choice practice test 3. So those of you that are doing a lot of practice tests and you might end up getting to practice test 3, maybe don't watch this video if you think you're going to do practice test 3. Make sure you watch it after practice test 3, or you're really not going to get anything out of it because you're already going to know the answers. All right, so this is multiple choice practice test 3. So just want to go through the test, tell you, the way I'm thinking when I'm answering these questions, and just kind of get your mindset, right? Remember, we want to be fast, but we also don't want to fall for any tricks or anything. So, all right. So let's jump into it. All right. So question 1, we got 0.5 moles of HE, 0.5 moles of NE. So we have equal moles of 2 different gases. They're in the same volume of container, same temperature. All right, so that means same pressure. So maybe the question is going to be asking about pressure, but no, okay? So what we have to understand is same temperature equals same kinetic energy. That means lighter particles move faster, right? So helium is lighter than neon, right? We have a periodic table. We could easily look up the masses, but helium's 4, neon's 20, so okay, you know that helium is smaller than neon in terms of mass. I shouldn't say smaller, I should say lighter. So this is asking what's going to escape faster, so that's effusion. But it doesn't matter if it's effusion or diffusion or whatever. We just know helium's moving faster, so it's going to effuse faster. It's going to diffuse faster. It doesn't matter. So HE will escape faster because its atoms are moving at a higher average speed. Yes, okay, there we go. We got it. Moving on. All right. So question 2, the lattice energy of a salt. So remember, lattice energy is just the strength of the structure. So lattice energy and melting point of a salt are basically the same kind of thing. So this is just an ion-ion question. Which ions will have the strongest interaction, right? Take the most energy required. It says, for which of the following pairs of ions is the energy that is required to separate the ions the largest? So which ions have the strongest interaction between them? So remember, the closer the ions, so the smaller they are, the greater the attraction, and the larger the charge, the stronger the attraction. So I know if I'm looking at A and B, I know A would be stronger than B because sodium is smaller than cesium and chloride is smaller than bromide. So that interaction would be stronger than that interaction, okay? And then if I compare C and D, I know C is going to be stronger than D because magnesium is smaller than calcium, and they have the same sized anion, so that interaction is going to be stronger than that interaction because of magnesium smaller. And then if we compare C and A, so A is the strongest between the negatively charged, the positive 1, minus 1 ions. C is the strongest between the positive 2 and minus 2. Now, which one's going to be stronger? It's probably going to be C because positive 2 versus positive 1 and negative 2 versus negative 1, but also magnesium ion is slightly smaller than sodium and oxide is smaller than chloride, so this is going to be very much stronger than any of them here, so C. All right, so moving on. All right, so we got a mass spec readout. Remember, these are the mass numbers of the isotopes. So if we looked at it, this is saying element X. So X has 1, 2, 3, 4, 5 different isotopes, 90, 92, 94, 96. Notice that the more abundant isotopes are over here, so that means the average atomic mass is going to be closer to here than over here, okay? But that's all this can tell me. It tells me nothing about ions or anything like that. It's just the mass of each isotope. So it's not going to tell me anything about charge, so I know it's not A. It doesn't tell me anything about valence electrons. That would be a PES diagram, which this is not. So it's either going to be C or D. We know the average atomic mass isn't going to be 90. It would only be 90 if this spike was 100% and we didn't have any other spikes. So it's got to be D. We've eliminated A through C. It's got to be D. And yeah, so the mass is going to be between 90 and 92. It's not going to be up here because these are less abundant than these. All right. So that's kind of an easy one. Let's go to number 4. So this is asking about an alloy. So remember, we're thinking interstitial or substitutional. So let's look at the structures. We know it's not going to be this one because that's an ionic structure, negative, positive, ionic. It's not this one. This would be covalent, and it would be a covalent solid, probably a polar covalent solid because the atoms are different. So it's either C or A. C would be substitutional, A would be interstitial, and since boron's a lot smaller than nickel, we would pick interstitial, so A. All right, so let's keep on rolling. All right, so, you know, AP being AP, they have to reinvent the wheel. So instead of dashed lines showing intermolecular forces, they're just showing a circle around the atoms that are interacting from this molecule to this molecule. So this is an IMF, and notice that the IMFs are coming off of Fon bonds. So here's the positive dipole of a Fon bond interacting with the negative dipole of that ion. So that interaction is a hydrogen bond, and the same thing's happening here, so hydrogen bond. All right, we go to here. Now we're going to have to do some math without a calculator. All right, so 200 grams of water starts at 50 degrees Celsius. It absorbs 8.4 kilojoules, and we want to know the final temperature of the water. So Q equals MCAT. The mass that we're going to plug here is 200. However, the energy we're going to plug in is not 8.4. We got to multiply by 1,000 because notice it's joules. All right, and so we're solving for delta T. So I'm going to solve for delta T. So I'm going to put joules on top, divided by the mass, divided by the heat capacity. So we got to do some mental math. 200 times 4.2, that comes out to be 440. Now this is pretty easy. 8,400 divided by 840 is 10. So the delta T is 10. So if we start at 50 and we change by 10 degrees, we're going to go up to 60. Now, the main thing here is to understand that the water would increase in temperature, not decrease in temperature. If it was losing this much energy, then our answer would be 40. But in this case, it was gaining that much energy. So we're going to go from 50 to 60. Okay, so let's go to the next one. All right. So we got 5 identical containers, so that means equal volume. You know, think about it. If you have more moles of gas, you're going to have higher pressure, that kind of thing. So it says each of these vessels are filled with N2 gas, okay, at 25 degrees Celsius. And so notice like vessel number 3 doesn't have any N2 gas in it, or doesn't have anything else. This is just going to have N2 gas in it. We have copper, we have iodine, we have sodium bromide, and we got sodium bicarbonate. So let's think about it. If you read the question, we're going from 27 degrees Celsius to 127 degrees Celsius. So we are increasing the temperature. So if we increase the temperature of this compound, when you have a polyatomic ion, it's probably going to decompose a little bit and form a gas. So the pressure in here is probably going to go up, A, because we're increasing the temperature. And so the nitrogen that's in here is going to increase the pressure, but also we're probably going to get more moles of gas. Here, sodium bromide is not going to melt at that temperature. That's too low. It's not going to vaporize. So the amount of gas in here is going to remain the same. The amount of gas in here is going to remain the same. It's just going to be moving faster because we're going to increase the temperature, so higher pressure. Copper is not going to vaporize, so no more moles of gas, but higher temperature. So higher pressure, and then 0.05 moles of iodine. Now iodine will probably vaporize, and so there'll probably be more gas in here too. Okay, so at 125 degrees Celsius, the pressure in vessel 1 is found to be higher than vessel 2. So pressure 1 is higher than pressure 2. So if if we kept equal moles of gas in these containers, the pressure would be the same in both of these, okay? But that must mean this, when decomposing, produced a gas, all right? And that's why it's higher. So which reaction produces more gas? Well, if we look at this is just producing more solid, so it can't be that. That doesn't give us more gas, all right? B, again, just produces solid, doesn't produce gas. C does produce a gas, 2 gas particles, okay? And D produces a gas, but notice it also consumes a gas. So D, you would end up with the same number of molecules of gas. You could consume a nitrogen, and then you would gain a C2H2 and ethine. So that wouldn't do it. So it has to be C. Now, this is where memorizing your predicting the products rules comes in handy. Now, AP says you don't have to do it, and again, because you don't have to memorize your predicting the products rules, that's the way I just kind of explained it, is the way you're going to have to answer the question. This produced more moles of gas, these two did not, and this produced a mole of gas, but it's replacing one. So you're not, it's a net gain of 0 moles of gas, right? This is a net gain of, 2 moles of gas, basically. So, but a thing to remember is when carbonates decompose, the gas you do get is CO2. So really, like this one, I could answer quickly if I remembered that rule. I just find the thing that's CO2 is being produced, okay? All right, so that's the first part of it. Now, these next questions go back to those diagrams, so we'll scroll back and forth. So at 127 degrees, the entire sample of I2 is observed to vaporize. How does the mass of the vessel of 127 compare to the mass of 27? So I2 vaporized, but understand, all the nitrogen that was in this and all the iodine that was in this container is still in the container. We didn't gain anything. We just gained more gas particles, but all the particles that were in here are the same number of particles of iodine and the same number of particles of I2, so the mass is the same. All right, this is kind of a trick question, but it's an easy one if we understand that, okay, none of the gas escaped, so the mass that we started with is the mass that we finished with, so the mass is the same, all right? So B. All right, so in vessel 3, so remember, vessel 3 was the one that just started with nitrogen and nothing else. And so you increase the temperature, so they would say what container would be, so this is what it looks like at 27 degrees, where the kind of arrows, the vectors represent the speed. What would the container look like at 127? Well, we didn't change the number of particles. Nitrogen's not reacting with anything. So it would be 4 particles again. So we need 4 particles. So we know it's not C or D, okay? So it's either gonna be B or A, and B shows shorter arrows on average. So that would be if we decrease the temperature. So it would have to be A. We'd have to have, on average, greater arrows. So A, okay. All right. So let's keep on rolling. All right, so an acetate buffer. So let's just understand, this is our buffer system, acetate and acetic acid. We are adding NaOH to it, so we're attacking it with strong base. Remember, what's gonna happen is the base will react with the acetic acid, and we'll lose this and we'll gain more acetate. Okay, and since we had equal amounts, if you go 50 milliliters of acetic acid and 50 milliliters of 0.2 molar sodium acetate, you have equal amounts of this, so it's going to start at the pH before the attack is going to start at the pKa, and they tell us the pKa is 4.7. So after the attack, we know the pH is going to be above 4.7 because we attacked it with base, so the pH is going to increase. So we know it's not going to be A, and we know it's not going to be C, because the pH has to go above 4.7. All right, so it's either B or D, and this is where we have to understand that if we're attacking this system with OH minus, we're going to lose this and we're going to gain that. So we're going to have more. We start out with equal amounts of these, but after the attack, we're going to end up with more acetate. So more acetate and a pH above the pKa, so D. Okay. All right. All right, so we have two hydrocarbons, ethane and butane. This is a bigger molecule. Um, and it's asking us which one has the higher boiling point and why. So remember, hydrocarbons are nonpolar, so the only thing they have is London dispersion forces. So the bigger the molecule, the bigger the cloud, the more polarizable it is, the greater the London dispersion. So we know it's either A or B. We're not going to pick C or D because that would be weaker. And we're not going to choose A because it says it has hydrogen bonding, and you can only have hydrogen bonding if you're polar with a Fon bond, but no Fon bonds and nonpolar, so it has to be B. But it says more electrons resulting in greater polarizability, and that means stronger London dispersion. And they kind of say that they're, try to think of all the different ways they might illustrate what London dispersion is they might say it's more polarizable, meaning at any given point in time there's a greater chance for it to be polar, which is kind of the same thing as London dispersion. An induced dipole is versus a permanent dipole. Induced is a random dipole-dipole interaction, which is London dispersion. Okay, so just kind of those things. All right, but that's a pretty easy one. All right, so ionization energies, first, second, third, fourth, fifth. Remember, immediately you're looking for the big jump. Here is the big jump. That means these electrons were in the valence shell and these electrons are in a core shell, so I know I have 3 valence electrons. Boom. There, I didn't even read the question. All right, so they say it's the second period, so we're looking at sodium's row, right? So we're, not sodium, lithium's row. Lithium, beryllium, boron, okay? So right now I know it's boron because I'm in the second row of the periodic table and I have 3 valence electrons, so I'm boron. So I didn't even read the question, it's just B, okay? But the first 5 ionization energies in their second period element are listed. Which of the following correctly identifies the element? So we've identified it as boron, so we know it's not C, we know it's not D. But the reason why we know it's not boron, the reason we know it is boron is because it has 3 valence electrons. That's what this is telling us, so B. So it's not, boron doesn't have 5 core electrons. That's not what this is telling us. This is telling us this element has 3 valence electrons, and since we know it's in the second period, it's got to be boron. All right, so let's go here. All right, so here I kind of, when I was first reading it, I underlined exothermic and I added heat here just in case, but I don't think I needed that to answer this one. But, that's a connection to make. So they give us the KSP. Which of the following changes will increase the solubility? So we want to drive the reaction this way. We want to make more of this dissolve. So we want to Le Chatelier's principle shift to the right. So if they said lower the temperature, that would be a way to make it more soluble, but they didn't say that, so let's look. All right. So remember, this is a Le Chatelier's principle, or no, it's not, sorry. This is just common ion. When you have a common ion, magnesium in this case, you'd be less soluble. All right. Remember, hydroxide is strong base. So if you add NH3, which is a base, you're not going to make more hydroxide available. This is kind of a common ion question, but it's not as direct. Adding NH3 to your solution would produce more hydroxide, and so it would shift the reaction this way. Increasing the pH means adding more hydroxide, so that would shift it this way. Decreasing the pH means adding acid, adding H+. If you add H+, the H+ is going to take out the OH-, decreasing the amount of hydroxide, and that's going to cause the shift this way. So when you're dissolving a metallic hydroxide in water, it's going to dissolve more in an acidic solution. So decreasing the pH is going to make this more soluble. All right, so let's go here. All right, so we got a heating curve. Let's just remember Q and S are about phase changes. Q would be delta H of fusion, S would be delta H of vaporization. P would be heat capacity of a solid, R would be heat capacity of a liquid, and T would be heat capacity of a gas. And this question is asking us, which of the following explains why the slope of segment T is greater than the slope of segment R? So it's kind of hard to see with the naked eye, but they're telling you T is steeper than R. And so remember, this is about heat capacity, not about molar heat diffusion. So we can go to C and D and cancel those out. It's not about the heat of vaporization. If we were talking about S and Q, we'd be looking at these answers, but we're not. We're talking about R and T. So they're telling you T is steeper because it has a greater slope. That means it has a lower heat capacity. So the specific heat capacity for gaseous ethanol is less than the specific heat capacity of liquid ethanol, A. All right? All right. So we got our polyprotic acid. This shows the dissociation of the first proton, the second proton, the third proton. Notice the equilibrium constant gets smaller and smaller and smaller. So, you know, they're already, the forward reactions of each of these are not very favored, but as we go down, they become less and less favored, all right? So we're mixing H2PO4 minus with HPO42 minus. You don't care about the sodium. And so 50 milliliters, 1 molar of this, 50 milliliters, 1 molar of that. So when you mix them, the molarity of H2PO4 minus is going to be 0.5 and the molarity of HPO42 minus is going to be 0.5. And because these reactions aren't very favored, you're going to keep these concentrations are going to be about the same molarities as they started with. So this reaction will happen and it'll make more of this, which is 1. So this will go up a little bit, but then this reaction will happen and it'll go back down a little bit, so they're going to stay around 0.5. And what are you going to get the least amount of? This, PO43 minus. You're not going to have much of this at all, so D. Okay. All right. So let's look at this. A certain gas, XY, decomposes according to this reaction. They give us our initial amounts, our initial pressures, okay? And they want to know which direction will the reaction proceed. So if we have too many reactants and not enough products compared to the equilibrium position, it'll shift this way. If we have too many products and not enough reactants compared to the equilibrium position, it'll shift this way. So remember, this is a Q calculation. Q is the same expression as K. So, all right, so we're going to do a Q calculation. We have 0.2 times 2 on top. Right, no, the coefficient's 1, coefficient's 1, so we don't have to square anything or cube anything. But this coefficient's 2, and so it would be 0.01 squared on the bottom. And this is where, you know, it gets iffy. We got to do the math. So 0.2 times 2 is 0.4, but 0.01 squared is 0.0001. And when you do 0.4 divided by 0.0001, you get 4,000. So Q is greater than K. We have too many products. The reaction is going to shift to the left to produce more reactants, so B. All right. So I'm going to stop there for this video. I'm going to come back later and I'll do maybe the rest, but we'll start it off the next video with question 17. All right.